If I asked you to identify this object in my hand, you'd likely say it's a pen. Even if you've never seen this specific pen, which is a special marker for light boards, it shares enough attributes with other pens for you to recognize it. In fact, you and most humans can recognize approximately 30,000 individually distinguishable object categories. Now, to train a deep learning model to recognize objects, we often turn to something called supervised learning, a form of deep learning. And that requires many labeled examples. Models learn by making predictions on a bunch of labels in a data set. These labels provide the correct answers or the ground truth for each example. The model adjusts its weights to minimize the difference between its predictions and the ground truth, and this process then needs a whole bunch of labeled samples for many rounds of training. So, if we want AI models to remotely approach human capabilities using supervised learning, they must be explicitly trained on labeled data for something like 30,000 object categories. That's a lot of time, cost, and compute. So the need for machine learning models to be able to generalize quickly to a large number of semantic categories with minimal training overhead has given rise to something called N-shot learning. That's a subset of machine learning that includes a number of categories. So we have few-shot learning, which uses transfer learning and meta-learning methods to train models to recognize new classes. Then we have one-shot learning, which just uses a single labeled example to learn. But what if we don't want to use any labeled examples at all? Well, that is the focus of this video, and that is zero-shot learning, where instead of providing labeled examples, the model is asked to make predictions on unseen classes post-training. Zero-shot learning has become a notable area of research in data science, particularly in the fields of computer vision and natural language processing. So, how does it work? Without explicit annotations to guide it, zero-shot learning requires a more fundamental understanding of the label's meaning, because after all, that's how we humans do it. So, imagine a child wants to learn what a bird looks like. In a process similar to few-shot learning, the child would learn by looking at images labeled bird in a book of animal pictures. Moving forward, she'll recognize a bird because it resembles the bird images she's already seen. But in a zero-shot learning scenario, no such labeled examples are available. So instead, the child might read a written story on birds and learn that they're small or medium-sized animals with feathers, beaks, and wings that can fly through the air. So she'll then be able to recognize the bird in the real world, even though she's never seen one before, because she has learned the concept of a bird. Just as even if you've never seen this pen before, you can still classify it because of its cylindrical shape, it has a tip, and that it's leaving colored markings when it comes in contact with the glass in front of me. And yes, there is actually glass in front of me. I'm not writing into thin air. Now, what I've described is one example of a method of zero-shot learning, a way to implement zero-shot learning. And that method that I've introduced is called attribute-based. So this is an attribute-based zero-shot learning method. That's where we are training on labeled features like color, shape, and other characteristics. Even without seeing the target classes during the training, the model infers labels based on similar attributes. So for example, a model can learn about different types of animals. So let's say it starts off by learning about stripes, and it learns about stripes from looking at images of tigers and zebras. Then it can learn about yellow, the color yellow, from images, let's say, of canaries, and then it can learn about flying insects from, let's say, just looking at, well, pictures of flies. Now, the model can now perform zero-shot classification of a new animal, let's say bees, despite the absence of bee images in the training set, because it can understand them as a combination of learned features. So striped plus yellow plus flying insect, that might equal bee. Now, attribute-based methods are quite versatile, but they do have some drawbacks. They rely on the key assumption that every class can be described with a single vector of attributes, which isn't always the case. So for example, like a Tesla Cybertruck and a Volkswagen Beetle, they're both cars, but they differ greatly in shape, size, materials, and features. Now, many zero-shot learning methods use an alternative method, and that is known as embedding. So an embedding-based approach to zero-shot learning. Now, this works by representing both classes and samples as vector embeddings that reflect their features and relationships. Classification is determined by measuring similarity between these embeddings using metrics like cosine similarity or Euclidean distance, similar to k-nearest neighbors algorithms. And because embedding-based methods typically process inputs from multiple modalities, like word embeddings that describe a class label and image embeddings of a photograph that might belong to the same class, they require a way to compare between embeddings of different data types, and that's where joint embedding space can help normalize those vector embeddings. Now, another method of zero-shot learning relates to generative-based methods of zero-shot learning. Now, if we think of the first example of generative-based, we have to think of LLMs, that's large language models. And large language models have a natural ability to perform zero-shot learning based on their ability to fundamentally understand the meaning of the words used to name data classes. LLMs are pre-trained through self-supervised learning on a massive corpus of text that may contain incidental references to knowledge about unseen data classes, which the LLM can learn to make sense of. And then beyond just LLMs, another zero-shot generative-based approach is my favorite type of neural network, and that is a GAN. GAN, that's an acronym for Generative Adversarial Network, and it actually consists of two competing neural networks jointly trained in an adversarial zero-sum game. So there's a generator component that uses semantic attributes and Gaussian noise to synthesize samples, and then there is a discriminator network as well that determines whether samples are real or fake. Fake meaning they were synthesized by the generator. Now, feedback from the discriminator is used to train the generator until the discriminator can no longer distinguish between the real and the synthetic samples. That's perfect for generating synthetic data that mimics the attributes of unseen classes, thereby enabling models to learn from these synthesized examples as if they were labeled. So that is zero-shot learning. It's something you do effortlessly every time you see a new object, and it's something deep learning models can be taught to do as well. Zero-shot learning shows AI's potential to generalize from minimal information, saving time, compute, and the hassle of labeling data.